Hello. Hello. I'm audible.
Good morning, sir.
Good morning.
So, okay, sir, you wait 5 minutes. So, we will give you some introduction regarding you. So, good morning, sir. Good morning, participants. So, welcome to the day 3 session 1. So, now I request Nagamani madam to introduce about the today's speaker.
Thank you, sir, for giving me this opportunity. Dr. Mahendra Kumar has been graduated his BTech degree in Electronics and Communication Engineering from State Government Rajasthan Technical University, Kota. He completed MTech in Specialization of Control and Instrumentation Engineering. He awarded PhD degree from the Department of Electrical Engineering, Indian Institute of Technology, Roorkee. He worked as an assistant professor, HOD, and R&D coordinator at Datamega Institute of Medical Sciences, Savangi, Varda, India. Currently, he is working as an assistant professor in Instrumentation and Control Engineering Department, Dr. B.R. Ambedkar National Institute of Technology, Jalandhar, Punjab, India. And he awarded by Gold Medal for Excellence in MTech by Rajasthan Technical University, Kota. From research point of view, published research work in IEEE Transactions, IET, Taylor and Francis, and Springer Journals. And area of research interest, robust and resilient control, intelligent control, PID control design, PIDA control design, and its applications, polynomial control design, stability analysis, time delayed and uncertain systems, load frequency control, power system stability and control, microgrid, reinforcement learning, cyber physical system and control, soft computing, digital image fusion, and image water marketing. Thank you, sir, for giving me this opportunity.
Thank you, madam. So, now I request speaker, sir, to start his session.
Hello.
Yes,
Hello.
sir.
Audible, na?
Mahendra Kumar, sir.
Yes, I'm audible.
Yes, sir. Yes, sir. Now you can share your slides.
Okay, no issue. So it is visible?
Yes, sir. Yes, sir.
Okay. Thank you to all. Yeah. Just a minute. Okay. So good morning to all, and I just say thanks to FDP organizers and Lindy College organizers and administration, as well as the organizers of this workshop, FDP program. So I'm Dr. Mahendra Kumar. I'm currently working as a system professor in Department of Instrumentation Control Engineering, also associate faculty in the Department of Center for Energy and Environment at NIT Jalandhar. So today we discuss regarding the robust control design. It means how do we can design our controller in terms of the robust performance. Another way, its application in the power electronics converters, like a DC-DC converter, we can discuss in the as per the application. Otherwise, also we have some more work like load frequency control in the power system, and other work in the cyber security also I had in the previous. So we can discuss these things today in our discussion. Okay, no, thank you. So so this is regarding today's our discussion points. Okay, now so currently one of the PhD students in my team, and one of the MTech scholar, and others BTech scholars, BTech students also. So my team is work on the robust control design, cyber physical systems, and in the power system, and another part AI. Okay, so this is my research team. Then my collaborators from the different institutions, my supervisors, my some colleagues, and some PhD colleagues, or maybe the friends. Now, so regarding my education, they have discussed in initial introduction, they discuss more and in better way. Thank you. Now, regarding my experience, they also mentioned that. Now, about the other things also. So if you go with the IEEE Student Travel Award during my PhD, recently my student also received the Student Travel Award from IEEE. Also, one of my student got the Best Paper Award from IIT Madras also in conference. So these things I have not mentioned here. These are some of the work which is I mentioned here and which published. And these are some reputed conferences. As per the conference, also have some weightage. So these are some valuable conferences. Some collaborated work which is ongoing and done. So these are the things. Some recently worked and some of the published is not mentioned here. Okay. Now, so these are some of the hardware where I done my work. Okay, like DC-DC converter. I started my work with the first. My work is published based on the power electronics, power converter, DC-DC buck and boost converter and buck boost converters. Okay, so this is a real-time hardware prototype of this DC-DC converter with the D-space controller. Here we use the D-space controller in our design. So this is a whole picture of this one. Now, this particular hardware is available in the control system laboratory at IIT Roorkee. Actually, when I completed my PhD, so I have done this work there. Here in NIT J also, I'm started to implement developing my lab. So we are purchasing the things here. Okay, now, so this is another hardware which is I worked like tune rotor, two input to output aerodynamical system. It is just mimics of the helicopter. Okay, this is mimics of the helicopter. These type of hardwares also have the power electronics like electronics things. So here also importance of power electronics. Also we have worked with the DC motor, Qincer DC motor also for the velocity, speed and position control, and also the inverted pendulum also inbuilt with this. So we worked with these things. Okay, so Cube Servo 2 is available earlier. Now it is replaced with the Cube Servo 3. If you anyone purchase, then you can go with the Servo 3. It has a very wide application in the control perspective. Okay, now, so why we need to go with the control? Because today discussion regarding control system. So first we need to go with the where is the problems in our physical or in the our real time systems. There we need to control system. Okay, so there is a lot of places and here and there. You always seen your near too much near everywhere there's some control action. Okay, and every system have the highly nonlinear. Most of the systems are nonlinear in our nature. Okay, and in our here and there. So in such a way, we need to do some exercise on these, and we can get our outputs. Okay, so some of the system like I discussed here, smart grid. Okay, it has the wide variety of the utilize the wide variety of power electronics converters. Okay, now another humanoid robots also robotic system also require the your power electronics converters. Your all the in medical field also we are designing some instrument. These instruments also require the power electronics converters. Okay, now another field from the agriculture perspective. In the agriculture also we are ongoing going with the cyber physical systems. Here I have showed the one of the picture. So these all systems also require the whatever the system we design, we need to power electronics components or power electronics converter somewhere for power supply also. Okay, now in aerospace also similar missile guidance everywhere. So wide application of the power electronics components as well as the power electronics converter in the world. Okay, in the domain of industry, in the application of society. Okay, everywhere. Now, so what will be the problem with these systems? Actually, whatever the system we seen every day near to us, they have some of the problems. Like, okay, some external problems, some internal problems. Okay, so key problems. What are the key problems in the systems? Like external or internal disturbances. Okay, there are noises also in the measurement sensors. From sensors, we get some noises also. Parametric uncertainty. It will internal parameters also change due to the aging. Non-linearity in our dynamics. Cyber attacks also currently the trending area like cyber attacks. Okay, now time delay in the communication. Sometimes the time varying disturbances, stochastic, like in the power system we are mostly in renewable system we are thinking about the stochastic nature of the low renewable. Okay, intermittent nature, and also stochastic nature of load demand in the power system. Okay, whatever the power system we have the power grid, but the demand of the your load is changed frequently. Okay, now, so these are the problems. But if you design the any control or maybe any system, and we are discussing some basic issues, we can handle these issues. Okay, we can handle these issues in terms of, if we have the system stability, fragility problems, there is some fragility issues also. If you make our system non-fragile, robust system, we made our system robust, then it's more better, resilient to cyber attacks. Okay, or any anomaly in our system, so we can make our system resilient, and adaptivity and the intelligent. So we need the all these things in our system to make more better. Okay, so these all things are not we achieve in that single way. Okay, single way we can't achieve. So we are maybe the sometimes hybridizing the things. Like we always need to stability, we need to non-fragility, we need to robustness, but from resilience, adaptivity, and intelligent, we need the different approaches. Okay, now, so here I one of the picture I mentioned here, control theory maps. It means the lot of control approaches are designed in the literature. Okay, in the literature, and in the renowned professor are develop some algorithm. So every domain, the control theory have the application. Okay, so based on these application, the different theories are introduced in the literature. So which is I just mentioned here. This particular diagram is taken from here. Okay, this particular link. Okay, now, so we can go with the next slide. So we are handling these problems, so we need to have some control. So control perspective is what? Whatever our desired response we want. So sometimes system is not give us our desired responses. Individual systems can't handle the some disturbances, parametric uncertainties. So that's why we need the control for the our desired response. In such a way, from industry perspective, initially the controllers start with the on off control, like a switch you heard about. Relay is also part of the control. Another things like you can go with the from industry like PID control. PID control is widely used in the process as well as in the power industry, in power converters also. Okay, so PID initially, if you discuss regarding the application perspective, so like 70 to 80, 90% control loops in the industry, in process industry, especially in the from 80 to 90% from the P or PID type. It means PI or PID type controller. Okay, control loops are there. So PID control is widely used in the industry application. Okay, and power electronics also it's have the application, because I have designed the PID or PID type controllers in the my DC converter design. So why we are mostly refer it PID controller? Because it have the simple design. It has the three parameters. Okay, like KP, KI, KD. So KP is simple gain. Okay, like amplifier gain. Then KI we can go with the some integration, and KD is go with the some differentiation. Okay, so different differentiator you can design through the op-amp also. Is an integrator you can design with the op-amp for transistors also. So these are all the things are developed earlier, or very simple structure. Okay, now another things like low cost. There is a costing of these development is very less as compared to other things like HMD converter you can go, or maybe MPC you can go. In other type of controllers it is low cost. Availability of the various design algorithm, it means the for tuning of the PID controller is various algorithms are available. Due to the reason is banned that because it is used from the last many years. Okay, that's why. And easy maintenance, because who are using this, they easily maintain it. Okay, maybe after understanding of the algorithm, it will handle very easily in the industry also, or anyone who use from their particular application. So from the PID controller basically enhance your system stability as well as damping of the control system. If there is any oscillations or maybe the overshoot issues, then we can go with the PID design also. And stability issues also we can resolve. So one of the basic structure is given like a US, a mathematical expression is given here, like you can see in the equation 1. Okay, so this is the one of the equation KP, KI, KD, and we can design the PID controller for any application. Okay, like sometimes KD is 0, but PI you can design for any system. Sometimes response is not appropriate, but you can design. So from design perspective, you need to only the tune the KPKI KD, whatever the value you can select based on this, you can get your responses. So if you select the KPKI KD in the best way, it will as per your desired specification, then you will get the your desired response. So it is the beauty of the PID control. Okay, now so definitely everything, nobody perfect, no. So in such a way we can see PID controller have the many advantages, but in such a way some limitations also. So limitation perspective, if you have large time delay in the systems, then PID control is not give the proper response. Sometimes we consider like the time varying disturbances. Okay, so there is also issue, because time invariant systems we can go, and if the time bound systems or time bound disturbances we can discuss here, then it is okay. But time varying is continuously varying with the, then it have the some issues. Okay, now design for higher order systems are complex, because analytically design is available for the second order systems. Okay, why? Because PID, whatever the second order system, we can directly design in analytical way. We can find the KPI, KDV in terms of the system parameters. So we can design for second order very easily. But if there is a higher order system like second, third, like third, fourth, fifth, or maybe 100 order system, then we need to go with some trial or error. We need to go with some empirical methods or some of the optimization approaches. But another way, then we can't say the our results may be the appropriate. Okay, another things, if we go with the reduce order modeling, like we can reduce the model of the system. In such a way also we approximate our model, and we can design our controller, and we can get our responses. So in this scenario, generally we can see in the process or in process control, or maybe the industry plants, they have the most of times first order or second order modeling in the approximation way. For the controller designing perspective, they have also some time delayed also. So time delayed first order or time delayed second order systems mostly used in the process control for designing of the controller. Okay, because easily we can design our controller, and we can apply this controller for the real time system. So we can get our approximate results most of times. Okay, now, another part from the problem is the tuning of the PID gains. So, is the main task for researcher to obtain the desired response for nonlinear system, autonomous system, and power system, because these are the highly nonlinear systems. So there is some tricky way, or you can go with some mathematical terminologies, proper way, proper mathematics, highly complex mathematics. Then you can get your beautiful results. Okay, but if you go with the highly complex mathematics, then understanding of the your process, designing of PID is tough. So what we can do, we can go with some simple mathematics. Okay, and through this simple mathematics or simple approach, we can design the PID for any type of system. Okay, done. So in such a way, there is one of the scope where I started my work. Now, so some of the example, if you consider here, I consider one of the integral system, third order integral system. They have the two poles at origin. Now the root locus of this plant is mentioned here in the figure 6. Okay, if you see here, then it is unstable. Okay, but if you go with the PID controller design like that here, like, so it is, this is a one of the design which is we have taken from here. It is dominant pole tuning approach based results. So this is the results as mentioned in the figure 7 as a open loop control design. Okay, open loop control system, GPID GC, loop gain. Okay, so in loop gain we also get the root locus not appropriate as per our desire. So also the some responses are beyond. Okay, now so how do we can handle it, such type of systems, how do we can handle it? Sometimes we can approximate the system in the first order or second order, and we can design our PID. So we can get sometimes results, but in the all disturbances we are not getting our proper response. So how do we can handle this? So in this terminology, PIDA controller is also designed. So PIDA is basically my work where I extended my work for PIDA controller, and do a lot of work in this area. So currently I'm working on this PIDA controller. So PIDA controller has the PIDA. PIDA everybody know, but DA is nothing but acceleration term. Acceleration term where we required, where we need to accelerate our response. Okay, minimize the error with the acceleratory, or maybe we need to quick responses. Then we can go with the acceleration term. Okay, otherwise you can go PI, PID, or PIDA, no issue. So PID plus DD, it means double derivative, also called as a isolation, or sometimes some people mention double derivative. So different researchers use the different maybe the nomenclatures like that. So it is just a variant of PID. So PIDA is first time introduced by the Junk and Dorff in the 1996. You heard about the Dorff. RC Dorff is also at the control system, very good book. Okay, so he first time maybe introduced this terminology. But sometimes when we put this point, this particular PIDA control discussed first time in the Dorff. So some researchers also have the some query some conflict. They mentioned that I also worked on these things, but I have not given the name. So it is your problem, na? You are not giving the name, so it is not yours. Okay, you done the work, you are not patent your work, then it's not yours. It is current trending era, na? You done the work, you are not patent filing, you are not got the maybe the grant, then someone maybe do or publish some work, then it is maybe the name of this particular person. Okay, so there is a issue sometimes. Okay, so first time PIDA is introduced by the Dorff in the 1996, as they are mentioning in the first work. Okay, now, so general theory, like we also always know that if you add the extra zeros in the system, then it's improve the stability and damping. In this particular concept, we use and add the isolation term in the PIDA. Okay, so this is expression of the mathematical expression of the PIDA controller. Okay, so it has the four terms, like PID has the three terms, PIDA have the four terms, KP, KI, KD, KA, or K also here the four, it means four parameters. So you have the more degree of freedom. Okay, what will be the benefits, like from the more degree of freedom? So this PIDA controller provides more degree of freedom in designing, also satisfy more design constraint or specification of the control system in comparison to PID controller, because of the more unknown coefficient, because it has the four unknown. So you can satisfy at least 3-4 constraint, which is based on your system requirement. Another things, like we can go from research perspective, it has a two derivative terms, so it is also challenging task for the peoples how to design and how to handle it. Okay, so in such a case, we can go and we can handle it. Okay, first we can go with its application, and then how do we handle these challenges also. Okay, so we can discuss these things. So this is one of the example which is we consider in equation 4. Okay, there we consider the say third order integral system. Okay, so for this system, if you design the PIDA based on the dominant pole placement approach. Okay, so now, so in retention, dominant pole retention approach, we can say. So in such a way, we design the control, this PIDA controller for similar system, and we are getting the root locus from, you can say, for most of the perspective, this controller handle the system. Somewhere it's okay, sometimes it's some gains not okay, but some part, most of the part is handle out. So sometimes what happening, whatever our issues in the system, we can handle by the whatever the we know. Okay, and we try it, but sometimes we are not getting the responses. So in such a way, we can forward or maybe the move on in the next step. Okay, adding the some extra structure, or we can add the some components. So in this way, we can maybe sometimes handle out our things. So as per the research currently, you can see in the hybrid controller designing. Okay, input two degree of freedom, 2 degree of controller 2 degree of freedom controller designing, or maybe the other control structures. So people are doing work in such a way and getting the responses. But if some particular controller will give these responses by the single design, then it's more better. Okay, now, so research, if we go with the research problems, like, so PIDA initially, actually I started work on PIDA, then the very few applications, very few tuning algorithms are available on this. So from this, I also work with the coefficient diagram method. My one of the collaborator is my one of the best friend work on the dominant pole, like multiple retention of dominant pole approach. And Kitty and DOP is initially DOP is proposed by the DOP. Kitty is also one of the method, gain margin, phase margin related thing, but it is not worked. Okay, and optimization algorithm, you know that everybody apply the optimization everywhere. So in this way also apply here. But from results perspective, if you change the some parameters, okay, in uncertainty also increase, sometimes on delay, then sometimes these algorithms may be failed, or we need to tune our system again. Okay, from the application perspective, also very few applications of this PIDA controller is available in the literature. So in such a way, also I extend this work for the load frequency control. Like load frequency control I extended, but another thing, DC-DC power converter. So this is the first time I introduced PIDA controller, or maybe the similar type of controller. It is one of the structure in the DC-DC converter. Okay, so from another problems, like from designing perspective, like coefficient diagram method I apply the internal motor control. I apply also automation, but I'm not satisfied most of times with the optimization perspective, because we need to again tune. We have the sometimes more and more trials and error. Then we can check the results. Okay. Now, so research. These are some research objective which is mostly related with my load frequency control in the power system or microgrid systems. But our basic work is regarding the today discussion regarding power converter. So we can up to we can discuss. Okay. Now, another perspective, from application of the LFC or AGC from Indian power system perspective, the AGC, LFC, whatever the power system have the power electronics component lot of. So as in the current scenario, also power system is integrated more renewable energy in the power grid. Okay. So in this way, it means that power electronics renewable energy systems, all the power energy sources have the inbuilt power electronics converters. Okay, whenever you integrate with your grid, your system renewable energy source systems, then you need to interface with the power electronics converters, power electronics systems. Okay, so it always requires the power electronic systems. Okay, then at case of the grid interconnection, okay, interface. So from this perspective, like load frequency control, so what happening, so more dominating with the power electronics components or power electronic systems, then our problem of the inertia or frequency problem is more. Okay, so my basically work is related to handling the frequency issues. Okay, in terms of the microgrid, or in case of the interconnected systems. Okay, now, so these are some of the way. Just a minute. So first we can discuss regarding the some CDM. CDM is nothing but coefficient diagram method or approach. Okay. So first we can go with the some approach. Then we can design our controller and we can apply in the DC-DC converters. Okay. So like the generalization of the coefficient diagram method we can discuss here. It means the most of designs are available for the second, third order sometimes, so a specific application problem. So I extended this for the nth order system also. It is somewhere available, but in my perspective I done in some different way. Now, CRA is also extended work of the CDM. CRA is also proposed in the literature also, but what I did in my work, I the basic designing parameter in the CDM or CRA. Okay, I select in terms of the robustness, from the in terms of the maximum sensitivity. Okay, or maybe sensitivity coefficient. Okay, so there is I involve my perspective or propose the things. Okay, now fine. Another things, based on the CDM, I initially work with the polynomial control design. Polynomial control design, maybe you can design for second or the third or the fourth order, any type of system. Your controller is polynomial. So in this way, I consider second order because my DC-DC converter, like buck boost or buck boost. Okay. So first I think about the buck and boost. So buck boost might have the second order system only. So in this case, I design the polynomial in the second order control structure. Okay, so we can discuss regarding the second order control structure. Okay, now also I will just tested the similar design, whatever I design the controller, it is for second order, any type of system you can test this particular controller. Okay, so like I apply for the first order unstable time delay system, then buck and then boost. The buck converter have the easily controlled. Okay, there is the only issue of the load changing, continuously load changing. Okay, there is nothing else. Okay, it is easily controlled by the our control algorithm. But problem with the boost converter have the non-minimum phase part. Okay, so non-minimum phase part is it have the tds to control it. Okay, so in this way also I worked, and similar designing handle out the buck and boost converter in a single way. Okay, so this is the first work which is I published in the regarding the DC-DC converter. You can see here. Okay. Now, so CDM is first time introduced by the S. Manabe in 1998. Okay, here also one of the theories is discussed regarding the CDM or polynomial control also. Okay, or coefficient diagram method or algebraic design method. Okay, so basically this work is started in 1952 or 1950 around. Okay, there is a one of the book available, p like so sorry, for name I just missed, but PS or something like Naslin. Okay, some researcher surname is Naslin, I think. So he introduced the one of the book and discussed the some of the theory, but they have directly not mentioned that this is a one of the methods and we can design the thing. There is a they discuss little bit theory, but finally extension or finally formulation done by the Esmanabe. That's why this CDM is introduced by the Esmanabe in 1998. He published some work in the 1996 also, but directly coefficient diagram method he basically from application perspective also given in this paper. Okay, now so CDM is nothing but it is algebraic or polynomial control design approach. Okay, it means you see in the classical approach, you see in the modern approach. Okay, classical based on the transfer function, modern based on the your status space. Okay, but what happening in case of the if we use the both the things togetherly. Okay, okay, done in such a way we can go with the algebraic or polynomial control design approach. So like classical control approaches have some issues. Okay, done, like or modern control approaches also have some issues. Okay, from some designing perspective. So this CDM have the both the properties and handle it both the problem. So the important feature of control system design is that it has the simple design steps, set point tracking and disturbance rejection capabilities, both the capabilities like set point tracking or disturbance like servo or regulatory control. Okay, so the basic, the main key point in the CDM is the characteristic ratio, is the characteristic ratio. Okay, this characteristic ratio is the main design parameter in the CDM. If you select these parameters values in the appropriate way with satisfying the stability constraint, then you can design the controller based on the CDM for any type of system. Okay, and you will get your desired responses. Okay, now fine. So in this approach, the characteristic ratios and generalized time constants are used in the transient response. Mainly what happening from initial time domain response also we say we think about transient response. Okay, so initially how do we can regulate the fastly transient response. Okay, done. So your characteristic ratios mainly handle with the your transient part. Okay, generalized time constant also with the speed, rise time or settling time also. So settling time we can go with the some generalized time constant perspective. A characteristic ratio you are handling your overshoot or sometimes regarding these perspective. Okay, so these two important parameters which is we discuss. Okay, now so here we consider one of the generalized system transfer function like nth order in the equation 7. Okay, and generally we consider these are the real parameters and the n is always greater than m. Okay, for the perfect or okay, ideal perfect or perfect in the system, or maybe sometime imperfect transfer function. So imperfect when the your numerator is more, denominator is less. Okay, degree of, so in such a so perfect we can go with the degree of the numerator is higher than the degree of the denominator is higher than the numerator. Okay, in such a way. From other things like transfer function of the controller we consider like nth order also similar way. Okay, real coefficient. Okay, now fine. Now so this is a system, this is your controller. So then we can form the one of the closed loop characteristic polynomial, like the 1 plus GS uh, GS is your plant, CS is nothing but your what, controller transfer function. Okay, so based on you can form this the target closed loop characteristic polynomial. Okay, 1 plus GS. So you can put the GS is just nothing but you are the NS upon DS, or controller is have the NCS upon DCS. Okay, so if you simplify it, then you can get the DS DCS plus NS NCS as a P target. It is just a polynomial. If you go with the characteristic equation, then you can put the 0 equal to 0. Okay, there is no issue now. So this is mentioned in the equation 9. So here we have the P target, like I mentioned this P target. So this P target have the some controller parameters also. Okay, unknown controller parameters. So we need to get these controller parameters. How? Okay, so the basic objective is to determine the unknown parameter of controller which satisfy the desired display, like overshoot and your settling time. So if in equation 8, if we go with the integral control action, then we can put the L naught is 0. L naught is 0. Then you simply get the your 1 upon S. It means you have the integral part is also there. Okay, otherwise also integral part there, but L naught is very less values. Okay, now. So another perspective, how we can get the unknown values. So for this, we form one of the desired closed loop characteristic polynomial from our side. Okay, this is the polynomial which is we frame from our side, like equation 10. So here Pi is the coefficient of P desired, or NP is nothing but the order of the P target polynomial. NP is nothing the order of the P target polynomial. Okay, so by comparing the equation 9 or 10, you can see here by comparing the equation 9, there is unknown parameters. Here each and everything is known, so you can compare the both equation, then you are getting the your unknown values of the controller. Okay, so here you can get the your values, but whatever the values you are getting, it is in terms of the like Pi, or Pi in terms of the characteristic ratio or the generalized time constant. So what is the characteristic ratio or generalized time constant, we can discuss here. So this is the one of the formulation which is introduced in the literature, like gamma is nothing but the characteristic ratio, or it will calculate it in terms of the Pi. So sometimes if you know the Pi, then you can directly get the your gammas. If you don't know the Pi, then you can change the formula in terms of the gammas. Okay. So tau is nothing but P1 by P0. But if you generalize the tau, generalized time constant, say it is based on the settling time. It is generally based on the settling time. That's why it is basically related with the steady state response. So TS is a settling time, then you are dividing by the like 2.35 or 2.5 to 3. Okay, so you can check there, no issue. Time constant, you can settling time, you know it. If you relate with the time constant also, TS is nothing 4 upon sigma zeta omega n, you know that for the 2% tolerance. Okay, so in such a case, you can frame this, it will get the similar perspective. Okay, so this is why this generalized time constant formulation is held here. Now, another part from the if you know the tau and gammas, then you can directly find your unknown coefficient of the polynomial, like desired polynomial, closely polynomial. So you can find the Pi in terms of the gammas or tau. So you need to frame initially gammas, select choose your gammas and tau in terms of your desired specification. So this is a one of the final formulation in terms of the gammas and tau for the P desired. Okay. So you can compare the Pi and you can get your results. So okay, here one of the questions maybe sometimes rise in your mind. Okay, if we select the gammas any value or tau any value, then we can get our desired response. No, we need to select these values in some particular certain condition or satisfy some certain constraint. So you can see here in theorem 1, I mentioned that some of the relation constraint also mentions. So gamma 1, gamma I plus 1 root of it is always greater than 1.4656. Okay, is given in 15. And also gamma I is have the relation with the it is previous value or coming value. Okay, so in such a way you can satisfy these constraint, then you can get your gammas in a proper way. Okay, these constraints are need to satisfy first, then you can select whatever value you select, you can satisfy these constraints. If these constraints are satisfied, then you can get your controller design from the CDM. Okay, so what happening in the CDM initially when the Hesmanap is proposed it and done some work, they mentioned that the gamma one, like we have the gammas, no, lot of gammas, like gamma I. So gamma I have the I is from the 1 to n minus 1 and my np minus 2. Okay, so in such a way we can check. So gamma the Manabes is what mentioned, gamma 1 is 2.5 fix. Okay, for every application you can select 2.5 and the other gammas 2. He considers some different filter structure, like you Butterworth filter structure, Chebyshev filter structure, so these based on these structured, he select these values. Okay, based on the different approaches. But generalizely, he mentioned that if you go with the Butterworth approach, then you can select the gamma 1 2.5 or other gammas 2. Okay, so it is not the justified way. For every system, you select only these values, you are not getting your proper response. So what we can do? we can think something else. Okay, so in this way CRA is introduced. CRA is nothing but characteristic ratio assignment approach, characteristic ratio assignment of CRA. It is developed by the YC Kim, LH Kill, and the SP Bhattacharya in 2003, which is published in the IEEE Transactional Automatic Control. Okay, so from the designing perspective, we've seen that so every whatever algorithm you propose, there is a sometimes limitation or some of the loopholes. So another researcher who are more interested in your work, who will maybe the rectify these things. So in such a way, CDM problems is rectified in the CRA. So what will be the main designing or maybe the main addition of the
Yes, sir. Mahendra Kumar, sir. Sir, your voice is not audible. Okay. Dear participants, there is internet issue, so please wait 5 minutes.
Hello. Hello. I'm audible?
Yes, sir. Yes, sir.
Okay. Sorry. Actually, there is a internet is gone, so that's why you can enable to me sharing the screen kindly.
Okay, sir. Now we. Okay. Now you can share, sir.
Yeah, just a second. Yeah. बेइज्जती करवा दी है। Okay. So sorry for interruption. Actually, there is internet is electricity is gone, so there is issue. So no issue. We can discuss from our where we maybe stuck. We left. Okay, no issue. Okay, now fine. So we are discussing with the like CRA. Okay, now fine. I think I'm audible, and we can continue. Okay, now. So CRA. Okay, so CRA is designed for the like we they have considered one of the all pole closed loop transfer function initially. Okay, now this is a one of the transfer function. Then they consider like gamma's is characteristic ratio of the QS, like this is okay, this is characteristic polynomial. Okay, now so if the following two condition is satisfied, like gamma 1 is always greater than 2 and gamma k is always in terms of this particular formulation. So what happening in the CDM, we are selecting gamma 1 is 2.5 and gamma other gammas of the k like gamma k 2, always it's fixed. Okay, like Butterworth approach in the CDM. But in case of the CRA, what they introduce gamma is always greater than 2 and gamma k is always depends on the gamma 1. Okay, so there is a very good, we have the some particular method, we have the some particular mathematical way. So in such a way we can get our different values of the gamma k. Okay, but there is also one of the issue. What we need to select the gamma 1 in way of the trial or error. Okay, maybe 2.5, 3, 4, 5, 6, 7, 8, 9, 10. What value we can select? There is no particular way. Okay, so there is also one of the research gaps. We need to maybe do some mathematics or involve some another control approach, a control methodology and control algorithm, and we can find the value of gamma 1 in particular way. Then we can find the gamma k also. So here one of the analytical way is developed. Okay, so in this way I worked and find the gamma's all values in terms of the maximum sensitivity by the some some equations I just satisfy with the some methodology, and we can get the relationship between the gammas and maximum sensitivity. Okay, now so this work we can discuss in the coming of slides. First we can go with the CDM or CRA based controller design, polynomial controller, and its application in the DC-DC buck and boost converter. Okay, now fine. So like in CDM, the values of the characteristic ratios, like I earlier discussed, gamma 1 2.5, gammas is 2. Then extension of the CDM is CRA. And sorry, okay. Now, so like here I propose one of the polynomial controller based on the CRA. Now, so here we consider the one of the generalized second order system, like okay, second order from the A1, A2, A3 and B1, B2, B3. It is a generalized way. There is a, we consider all the poles, all the zeros, all the things. Okay, you can consider here this system. You can go with the unstable way. You can go with the non-minimum phase. You can go with the perfect transfer function. There is a stable system. Whatever you can make, you can frame the system from this generalized second order transfer function. So here we consider the one of the control transfer function like equation 19 GCS is like A2 K1 K naught L2 L1. So here we consider L naught is 0 for the integral perspective, because integral control, you know, the perspective of integral control to get your steady state response. Okay, achieve the steady state response. So that's why we consider this particular control action also. So in such a way we need to find the K2 K1 K naught L2 L1 unknown values, then we can get our desired response for particular, so whatever the system it have. Okay, no issue. Another things also, one of the beauty of this particular CDM based way, the pre-filter transform function is given like that. Fs is nothing but app gain upon L2 S square plus L1 S. It is your denominator of the controller, and app gain we can get at the steady state. Okay, like DC gain, you know, like in such a way we can calculate the app gain also. Okay, so we can discuss these things also, no issue. But here our system, this one, there is controller, and this is your pre-filter transfer function. It means that if you connect the controller with the pre-filter, okay, then we can say this particular structure as a 2 degree of freedom, 2 degree of freedom control structured. So we need to get the values K0, K1, K2, L1, L2. So this is one of the theorem. So here what we consider as the closed loop control system is asymptotically stable, and also have the capabilities of the reference tracking and disturbance rejection if the polynomial controller coefficient gain are have in this terminology, like K0, K1, K2, K3, K1, K2, L1, L2, and Z0, whatever Z0, Z1, Z2, Z3 is nothing but these are the values of the in terms of the gammas or tau. So our whole controller, it totally depends on the system parameters, gammas or tau. Okay, so if you know we know the system parameters always. Okay, as usual, then we need to select the gammas or tau better way, then you can design your controller for this particular system. Okay, so here from the application perspective, if anyone want to maybe go more details regarding this algorithm formulation or proof, then you can refer to my first paper, which is I mentioned here, IEEE tangible and industry application. Okay, if you require more details analysis, there is no issue. Okay, you can get the each and every step in the designing perspective. Okay, now so here we have considered one of the example, like illustrated example, design of proposed controller for the unstable non-minimum phase system. Okay, so this is the unstable system. Okay, this is the time delay. Now, so I have just a first order Pade approximation I have considered here. Okay, like 1 minus theta by 2 upon 1 plus theta by 2. This is approximation of e to the power minus theta. Okay, s. Okay, so in such a way we have considered like this one. Okay, so we approximate why because we need to go with the simplified transfer function. Okay, we are not dealing here is the time delay, we are approximate this time delay in terms of the transfer function approximation, and we are forming the one of the transfer function like that. So this transfer function have the instability, okay, as well as the non-minimum phase characteristics. Okay, both the way, zero is in the right hand side, poles also in the right hand side. Okay, so from theorem 2, which is we discussed earlier, so here we consider the gamma 1, gamma 2 and gamma 3 values in this way. Okay, these values from our formulas, and here we consider the cycling time 3 seconds for the system. So tau is a 1.2 second. Okay, from this generalized formulation, tau is nothing but the ts upon 2.52 till 3, whatever value you can select between these. So it will approximate 1.2. Okay, so in this way we can get the controller transfer function, feedback control transfer, NCS or DCS like that. NCS and DCS like that. So these are the values of the K2, K1 and K0, and this is L2 or L1. Okay, from these formulas. Okay, you can frame in the MATLAB and you can get the directly these values. Okay, then pre-filter is what? AppGain and DCS. AppGain and DCS. So AppGain, I mentioned it. Okay, from here, DC gain. Okay, 0.25, put all the values there, and DCS like that. Okay, you can do these things, no issue. Okay, now our results, main perspective is our results. People don't want to mathematics, don't want to in between what happening, what is the internal process. They want the response, everybody need the response, but from industry perspective, from your system hardware analysis, but from publication perspective, we need each and everything in our publication paper. Okay, now so design proposed control, like, so here we can go with the reference taking. Okay, so I compared the results with the other techniques also, and also I mentioned the 2 degree of freedom PIDF. PIDF. PIDF, it means PID D with the derivative low pass filter, like derivative filter, like we have write the F. 2 degree of freedom, it means it have the active pre filter also with the PID controller. That's why it says the 2 degree of freedom PIDF. So whatever the polynomial controller we design here, this particular designing, it's similar to 2 degree of freedom. It's similar to 2 degree of freedom PID. The response of the both the controllers are same. It means whatever the polynomial controller, second order polynomial controller I designed here, it is similar to 2 degree of freedom PID F controller. So if anyone designs the PID type controller for any second order system, then he will refer the this design or this approach. Then it will stable this design stable the your system, also give the your somewhere desired responses. Okay, not exact, but if you select the gammas in the proper way, then you can get your exact responses also. Okay. Now, so from tracking, we can see that the polygon or 2 degree freedom PIDF we have the similar response, but other have the some somewhere the rise time is more. Okay, their settling time is also more. So in such a way, another condition, if you go with the disturbance, you consider the disturbance at the step disturbance at t equal to 10 seconds. Then here one of the disturbance we create at the t step response. Okay, step disturbances we converted here, then we also get our response is better than compared to existing one. So what we predict that the simple designing. Okay, Pandey and Maji have the some different designing, Junk have the some different designing, but our polygon is very simple. We have the second order system. Very easily we can get select the gamma's value. Okay, based on the formula CRA, and our controller done, and we can get the responses for the unstable system also. Okay, with the time delay. Okay, now from this is from reference graphical way, you can get the results. Okay, picturization. Then from somebody say quantitative results, what will be the quantity? Okay, so from quantity analysis, we can go with the integral performance indices we consider here for reference checking and the disturbance rejection rate. So from integral performance indices like ISC, integral square error, ITSC, integral time scaled square error, IAE, integral absolute error, ITAE, integral absolute, okay, integral time scaled absolute error. CE is nothing but controller energy. C is nothing but controller energy. Whatever the controller energy is, just whatever you have the control out, okay, control output, you can just square it and integrate it like IC. Then you can get the your controller energy. Okay, so in this base I uh, calculate the controller energy here. Okay, other formulas IC, ITSC, IE or ITAE. So we from comparison you can get the like a polygon or 2 degree freedom has a similar response. Okay. Other have the some like ITA maybe somewhere high, somewhere low, or like that. From control energy perspective, if you see that polygon requires a little bit more energy in comparison to other controllers. Little bit more, not the much more, little bit more. But your responses is very good in reference tracking. But okay, here somewhere polygon maybe the need more energy. But from the disturbance rejection perspective, if you see from here, then you can compare with the others. Then we are getting the very good responses. Okay, from the integral performance index systems or from control energy also. So you can see that in reference tracking, somewhere the energy utilized by the controllers is similar somewhere. But in case of disturbance rejection, main issues with the disturbance rejection. So there the polygon design is use the very less energy, like half, somewhere half, almost, okay, almost half of the thing. So it is, that's why we can measure the controller designing in terms of the controller energy. Okay, or somewhere time variation. Okay, time variation indices. Okay, total time variation, we can say total variation TV is also one of the parameter which is evaluate the performance of your controller. So from control designing perspective, I see the controller require the less energy, also give the better responses. So both the way is satisfied. Okay, now from the stability perspective or sensitivity perspective, we can see that maximum sensitivity, one of the key point we can select here. And in this terminology, we have checked the compared to others. So here the MS have 3.98, 3.98, or Junk and Paddy have the some different value. Okay, so MS is what it say, like MS values is based on the your instability and your time delay. Okay, so here for the unstable system is also there, and non-minimum phase system time delay is also there. So in such a case, we have like a value of the MS is 3 to 6.5. This is the one of the range, 3 to 6.5. So in this range, 3.5 or 3. So we the all the will 3.5 to 6.5. Okay, all. So in this way, we get the our MS in the particular range 3.5 to like 6.5 something. So all the controller are maybe in this way, but if you MS is near to 3.5, then system is more stable. Okay, system is more stable and performance is also okay. Okay, but if it goes with the 6.5 around or nearby 6, then the system is very less stable and the performance may be somewhere better, but this performance is also not appropriate. Okay, so some of parameter we discussed like performance, then controller regarding, and the complete analysis based on the stability perspective or robustness perspective based on the robot maximum sensitivity. So these three terminology we discuss for the our unstable non-minimum phase system. Okay, now so definitely people are waiting for the power electronics utility now. So we have just discussed regarding the some basic non-ideal DC buck and boost converter proposed designing also. Now, so from the DC converter perspective, I also mentioned you in the power electronics is totally dominated in the modern power system or smart grid. Okay, so or from the interface grid interface also the your electric vehicles also have the some all power converter, others whatever the system you can see. Okay, it is most of systems are required the power electronics components or power electronics converters. Okay, so in this perspective, it affects the power system from the inertia perspective also. It reduces the inertia in the power grid, and we need to some another control in the power system also. Okay, also the one of the challenges also in currently people are facing in power electronics components or power electronics converter is the cyber attacks also. So we can discuss also this part here also. Okay, now, so in today's era of the modern power system, the smart grid and microgrid have been developed for the environment-friendly power generation operation control system. A rapid growth in users power electronic component in the grid connected or islanded microgrid is observed at in the both the way. You can go with the grid connected, grid tied, or maybe you can go in the islanded way or isolated way. Power electronics converters is required. Okay, in the solar, you know, you supply your AC to your system, so you need to converters. Okay, so every DC-DC converter also part of this. Okay, so DC-DC converter is the important circuitry to provide the regulated voltage supply to the loads. Okay, constant supply like we can say. Now, so the loading condition in the current power system are extremely uncertainty. So the uncertain loading condition lead to unwanted impact on the output voltage control of the DC-DC converter. Okay, so this necessary to develop the control scheme to deal with the inauspicious effects of the unknown uncertainty and the whatever the perturbation. Okay, now answer. So buck converter is highly sensitive to sudden change in the load. It is one of the limitation of the buck converter. It is highly sensitive to the your sudden change in the load. Okay, mainly it is main focused. Okay, so easily we can control this part. Okay, now so the major issue of the output voltage control in buck converter is the address. Now the main aim is to acquire tracking of the output voltage while also ensuring an acceptable smooth transient response. Okay, so this is one of the structured I have considered here. This particular designing is done by my one of the senior in the PhD. Okay, now he is part of the he is part of the my work, and he designed all the things. I just tested the my controller on here and understand the feasibility of the controller in the real time way. Okay, so this is one of the Siddhartha is my one of the friend senior, and he is currently working in the as a postdoc in the IT Kanpur. Okay, now so this is one of the designing simplest designing of DC-DC buck converter non-ideal. How to we can say non-ideality? Like we have the inductor, it have the some resistance. We have the capacitor, it have the some resistance. Whatever the diodes, because RD is here. Some switches also. Okay, supply also has the some resistance. Okay, and so everywhere we consider these are the non-ideally. It said that ideally it is zero. Internal resistance are whatever you consider zeros. Okay, infinite zero. Whatever as per the your perspective. Okay, now so in this way we consider non-ideality. It means we consider that these internal resistance also with the each component. So that's why we can say node ideal buck converter. This is your switch, this is your diode. So switching is the main constraint with the with with your control. Okay, everything your power electronics people are developed, but issue with the your switching perspective. So here the main switching perspective is the control perspective. Okay, so you can design any control algorithm with this, then you can control the better way you are switching of the power converter, then you are getting the your better responses during the reference change, during the your supply change. Okay, during your uncertainty in these components. Okay, during the parametric uncertainties. So load changes, so you can get your better response when the your switching is proper. Okay, so these are the some parameters which is we consider in the design, like input voltage like 12 to 15 voltage, source resistance is this. Just a minute, yeah, please. Sorry, not Mahendra Kumar. Means you can go at the sixth floor. Okay, sorry. So there is a source resistance. Is this inductor is like a value we can consider with their internal resistance also. Capacitor in similar way. Diode forward drop like 5.5 volt. Another parameter like that, and our main output is the 8 volt. So like buck, we have the condition that your input is high, output is less. Okay, so this is one of the condition. Another switching frequency, 20 kilohertz. Okay, 20 kilohertz we have considered like the switching frequency. Okay, so this is the simplest design like in transfer function. So what is N1, N2, D2, D1, D naught or K we have considered, and apply the state averaging method. Okay, so state averaging method, then we can get this transfer function between your output voltage. Okay, changing the output voltage with changing the your duty cycle. Okay, so these are the parameters we have. So we know denotes the small signal variation in the output and duty cycle. So we need to design the PWM block duty cycle condition like that. Z plus 0 to 1 denoting the on and off action of the switch. So main and to we need to acquire our tracking of the V naught with the smooth transient response. Okay. So here similar controller which is we discuss in the polynomial form we design here. So transfer function we consider from here non-ideal DC-DC buck combinator which is we discuss here this one. After putting all the values we get this transfer function like this is your transfer function. It is stable. There is no issue. Okay. Now, so the characteristic ratio values are considered like here from theorem 2, 2.5 gammas and gamma 3. Also the generalized time constant we consider here TS is a settling time you consider 2 milliseconds. Okay. So in such a way your generalized time constant O is 18 10 power minus 4 second. So based on these parameters we design our controller like that. Okay. This is one of the way. Now this is your controller transfer function and this is your pre-filtered transfer function. Okay, so based on this designing we can get our response. Okay, now so here we consider one of the some objective like regulatory control. You know that I mentioned earlier, maintaining output constant output voltage in present sudden change in the input voltage and also sudden change in the R load. And servo control problem is the with the reference set point tracking. Okay, we reference now. So here we consider some simulations. We consider a total 5 cases studies here. First is a nominal condition. It means your reference voltage is 8 or your input voltage 12 volt. Second condition we consider the sudden change in the input voltage. Sudden change in the input voltage. So the reference voltage is 8 volt and input voltage is varying as the V in first 12 volt to 11 at this timing 8 millisecond. Then V in change from 11 to 12 at the 1 point 12 millisecond we can say. Okay, now we can say that further the input voltage is varying from 12 to 13 and 13 to 12 in based on the this selected timings. Okay, 2 instant. Another case we select like the reference change. So we can change the reference from 8 to 10, 8 to 6, 6 to 8, or 10 to 8. Revert. Same timing if you consider 6 to 8, 8 to 6, 8 to 10, 10 to 8. It means variability we consider in the input and reference voltages first. Then another condition we select like the sudden change in the load. Like RL we consider like 20 ohm. Then we can convert it into 10 ohm at this moment and 10 to 20 ohm. Then we need to check our responses. Further parametric uncertainty in the inductor capacitor 10% or plus minus 10% or plus minus 20% parametric uncertainty in the L or C respectively. So based on the uncertainties in the L or C, actually during my work, when I started work and I consider this case study 5 during my work. So people ask me how you can consider this particular uncertainty in the inductor capacitor. Why 10%? Why 20% only? Okay. So there is a one of the incident which is discussed by my supervisor continuously. He totally asked why you are considering inductor capacitor in this range and why these are parametric uncertainty. So sometimes it's happened. We done the take the values somewhere and we put these values. Okay, done it. It's happened most of time. So why I considering plus minus 10, plus minus 20 parametric uncertainty? It is the reason behind it based on the tolerance. Okay. So here we have checked with the capacitors and inductors, and there the tolerance is given like that. This particular percentage of changes may be happened in the your capacitor sometimes or inductor values. So a tolerance based on so that's why I consider 10%, 20%. Okay. So if there is a tolerance is very less, okay, there's a tied value, it is fixed, very selective value, you can consider your L or C. Then what happens? Your cost of the converter is increased. If you go with the somewhere some literature is more, yeah, some tolerance is more, maybe the cost of the components is less. Okay, so components cost is less, so your economic components, your device is economic. So if your controller handle these things or maybe in this direction also, then you are not afraid of these things, like, so that's why the control importance is more in this perspective also. Okay, now, so these are the simulation responses we get. So this is output response of the proposed polyphone and the IMC PID with the different gain crossover frequencies. They design the controller based on the different gain crossover frequencies. And here we design the controller based on the single parameters, gammas, okay, or taux, okay, like cycling time, whatever you consider, you can get the gammas, taux. So from this response, we can get the our proper response. Like, okay, there is a settling time very less. Your rest time is also less somewhere. So all the perspective we can say there is no overshoot in the reference tracking. Okay, no. If you somebody say if your reference is changing from continuously from initial to lot of multiple stages, okay, like staircase changes, then in such a case also I change from the 4 to 5, 5 to 6, 5 to 6, 6 to 5 to 6, 6 to 7, 7 to 8. In such a case also the proposed controller and existing also work, but proposed controller track the properly whatever we seen in the single diagram, which is held here also in the staircase also. Okay, so it is show the robustness and action of the control. Okay, now perfection of the controller. Now from the rise time also we can say from simulator or hardware also. From simulation it gets less, but from the hardware also we can say that it is somewhere change. Because the controller total design somewhere in the tight values of the gammas. If you maybe lose, there is somewhere the little bit simulation time is increased, but your experimental time is also less somewhere. Okay, but from the whatever we design, we can get this. The IMC PID have the more maybe the somewhere the in the two condition where we are getting approximate somewhere approximate result, where the experimental results timing in a microsecond is similar way or maybe the less compared to 2.5 kilohertz, there is a less. Okay, and other perspective simulation also we get the better as well. So in the both the way, if you see that the control proposed control simple controller. Okay, okay, for all type of circuit board system, it will for the buck converter you can design, for boost converter you can design, whatever system circuit board you can design it, you can get the your responses in better way. Okay, from hardware also we check. So this controller design is okay. Now from the control perspective, it required the less, TV is total variation. It is from control like in the last perspective in last example we discussed regarding control energy. Then there I mentioned total variation. So total variation also one of the part to check your performance of your controller. Okay. Now from the MS also similar perspective, like maximum sensitivity. Like for this complete stable system, the MS from 1.2 to 2. Okay, it is standardized. Okay, 1.2 to 2. Based on the your phase margin, gate margin, you can check that. If you seen that. Now, so MS directly represent your gain margin, phase margin also. Okay. Now, so 1.4, it between in the 1.2 to 2. So this range gives your response in terms of servo or regulatory control. Okay, or from the stable or robustness, performance or stability perspective. But this IMC controller is more stable, but performance is less. Overshoot is high. Okay, rise time is also high. Okay, controller energy is also high. So their performance is less. Okay, now, so these are the responses in case of the sudden change in the input voltage. Okay, so like we can see, check here from 12 to 11, 11 to 12 voltage at the certain time duration, 0.008, 0.1, 0.012 seconds. Now, so in such a case, we can get the upper reference is properly tracking. In such a case, 12 to 13, 13 to 12 is also. In the both the condition, we get the better responses with the our proposed one and polycon like now. We can say another way, like from 8 to 6, like reference we can change, or 6 to 8, 8 to 10, 10 to 8. So whatever you can consider, your controller, design controller will track the responses. Okay, so this is one of the way we can analyze our controller performance from the sudden change in the load. Also, there is a very less disturbance in the your polygon. Okay, other compared to others. Now, from the plus minus 10% parameter consideration also, there is somewhere the variation in overshoot or maybe the oscillation in the other controllers, but polygon gives the some somewhere better responses. Okay, in the plus minus 10 plus 10% in the L inductor. In similar way, minus 20% in the current capacitor, plus 20% change in the capacitor values. So also the similar responses we get in the all the conditions. So these are the all the simulation responses, but we need to hardware experimental also. So in this case, whatever the hardware I show in the first slide, like hardware experimental there. So there I mentioned the hardware. These are the responses from this particular controller. Okay, this particular hardware. So in case of the nominal condition, we are tracking at our output voltage level 8 with the your rise time 600 microsecond. These responses you can check in the my paper also. And then in case of the input supply, we change. Okay, input supply we change here is from, okay. So input supply we change. Then also we can get our reference properly. Okay. Then if we change the your reference, also the take the reference properly in the hardware also. Then during the load also, then the attack, then the change the value, then some impulse, but after that it's properly at the there required. Okay, so these are the all the things we discuss. But in case of the controller, like parameter consider, we have not checked in the hardware because it is changed with the values is changed with the aging or due to the heating of the components sometimes. Okay, or other effects, internal effects, some physical effects also. So value is changing. So after 1 and 2 years also controller gives the response. So maybe 10 3 or 4 years somewhere. So you get the your responses proper way. Okay, so this is the complete discussion regarding the your controller perspective robust control design for the your DC-DC buck converter. Okay, now, so if you go with the some like another perspective, just a minute. Now, this is my another work with similar controller for boost converter. Okay, so I just show it is visible to all. Hello, it is visible now.
Yes, sir, it's visible, sir.
Okay, thank you, thank you. So if you go with the in the boost converter perspective also. So this is a structure of the boost converter, circuitry of the boost converter, non-ideal DC-DC boost converter we consider here. Now, so this is your diode. Okay, there is switching. Okay, so this is change of the some structure. Okay, in the earlier switch is here, diode is here. Now in this condition, your in boost converter, the switch replace the boost diode, and diode is come to somewhere else. Okay, now so in this structure you are getting to your boost converter. It means your supply, your reference, okay, is high, supply is less. Okay, supply maybe the you consider like your output may be the high. Okay, now, so what parameter we consider here, we discuss here. Okay, so this is the transfer function of the your boost converter. So what happening here, it is second order, but happening is there is a non-minimum phase nature because one of the zero is in the right hand side. So in this case, we need to design our controller. Okay, if we design the other controller, they have some IMC is left this non-minimum phase part and design only for this double perspective. Then we can't say that the every condition will handle by the IMC. Okay, so in this case, we designed our controller polygon for this particular system. So these are the values of the KVD or all other parameters here. So these parameters are mentioned here. Okay, now, so for this here also we need to regulate our control voltage. So here we design the controller, design similar. This is similar controller we design for the system also. These are the values. So input voltage is 5 volt and your output voltage is 8.33 voltage. We consider as a reference. Input 5 volt, output is 8.33. Okay, frequency is similar. Okay, load resistance is same, 22 ohm here we consider. Other parameters change as per our requirement. Now, so this is a proof is discussed in 14. So that's why I am not. Another way, 2-degree of freedom controller, how it's similar to your polygon, which is I discuss here. Okay, so we can go with this also. So here, like this is one of the diagram of the polynomial control design approach. Like this is your output, this is your system, this is your controller, and this is your pre-filter. This is your pre-filter. Agree? This is disturbance. This is your control input. Agree? So this structure is called as a 2-degree freedom. Then we can convert in the simple PID type converters control action. So then this is your system. This is your Y output. This is your disturbance. This is your PID as controller. Okay, PID with the PI with the derivative filter, and then this is your filter pre-filter. So this is structured called as a 2-degree freedom PID app. So this is the output of the this particular figure 2, and this is the output of the equation 16 is the output of the this figure 3. Okay, after simplification we are getting the this type of the response now. So from comparing the things, we get fs is nothing, fs is what, f gain upon dcs. Okay, or a PID is nothing, f gain upon ncs. So there is some similarity. Okay, but your designing is once you can design the 2-degree freedom PID F also. Okay, so there is a whole thing is similar way. Okay, now then how you can get KP KI KD? So KP KI KD you can get in this term KD KP KI or TF. Okay, TF done. So FPID is one of the similar perspective which is we discussed earlier here. So in this way you can get the your 2-degree freedom PIDF, or both the 2-degree PIDF or polygon is the similar in the responses. Okay, and designing of this is similar way. Now, so results perspective, here we can consider 2-degree non-linear DC boost converter. So here we consider this non-minimum phase behavior. Now, okay, so this is a transfer function. Okay, so sorry, this is a controller transfer function, and this is your pre-filter designing. Now, in case of the polygon, or in case of PIDF, this is one. So from the case study, we consider that here similar perspective. The output voltage 2-degree freedom PID based non-ideal DC-DC power converter. It means it is similar way. 2-degree freedom or polygon, both are the same. So here what condition, normal condition. Also, in case of the also polygon gives the better response as compared to other structure. Other different frequency they considered, but single design it gives you somewhere the approximate your desired responses. Okay, now but other way of INC have the lot of overshoot, or maybe somewhere the under or damped responses, or undamped responses much more. Okay, in case of the change in the input also we get the responses in similar way which as a nominal. For similar perspective for the reference change, in same reference change also we can track in the appropriate way with the our design. Okay, polygon is give the better responses. In case of the load change also we can get the response in simulation. Okay, so these are the TV. Regarding the, if you go with the some overshoot or like that in perspective experimental or way, so propose is give the simulation results like microseconds we are considering in the simulation, and micro millisecond in the rise in the experimental rise time. Okay, so here a little bit more, but the results are more better with the existing the proposal polygon. Okay, now so these are the responses from simulation. From TV perspective or MS perspective also our design perspective is somewhere better. But in case of the uncertainty, if you see, then also similar perspective, the polygon handle out the boost converter also in the better way. Okay, somewhere maybe the like in case of the plus 20 PU in the capacitor, it have the some peak, but it is settled down before. Okay, now so in case of the like hardware experimental results, we consider similar way. Hardware like your reference input voltage is 5 volt, your reference is 8.33, so nominal condition. So we can change the your input also. Okay, so it is a 5 to 4 or 4 to 5, 5 to 6, and 6 to 5. And in case of reference also change 8.33 6.5, and 6.5 to again 8.33, then 8.32 to 10 volt, and 10 to again 8.33 voltage. And also you can change your load also. So this is a hardware actually, which is I mentioned this is boost converter your. Okay, and this is hardware I discussed earlier. Now these are the responses from the hardware. Okay, 2-degree freedom, it means polygon similar way, no issue. So these are the response in case of the nominal condition. These are the in case of the your input voltage change. So there is also no issue. Your output is okay. Then if you go with the reference change, then also no issue. Reference taking and load changing is a similar way. So from the this perspective, what we understand that a simple design, we consider polygon polynomial controller, or it's similar to degree freedom PIDF. So it is handles same similar design CDM or CRA. It handles the buck and boost converter. Okay, or maybe such type of the unstable systems also. So that's why just whenever you start somewhere, some work, I just one of the my some of the key insights or key point for you. Whenever you start your work in the research point of view, you think the some easy things, which is maybe the use for the some generalization way, then it will from the paper publication or from the development perspective, for industry perspective, it will help you. Okay, now, so this is one of the way I mentioned for the polygon. Also I have worked with the PIDA controller based on the IMC for the boost converter, buck converter. These results I published in some conference. Okay, after that I stopped this work because I switched from the IIT Roorkee to in the Tameke, then Tameke to here. So I am developing labs. Then I will test it more controllers or more action on the similar way. Okay. Now, fine. If you go with the next way of the CDM, like CDM, CRA, then RCDM. So what I suggest, so we can select here the gammas value based on the MS. So here I design the select the gammas based on the MS, like in terms of this one. This is one of the formulation. This is one of the final output. Like whatever the gamma, I select based on the MS. It means MS is nothing but maximum sensitivity. Maximum sensitivity is based on the your system stability and performance. Like gain margin, phase margin is also one of the part. Okay, so if you select the best value of the MS from the particular range as per the your system, generalized systems, so you can select your gammas better way and you can design and you can handle any type of the system. So here I apply this particular design for the hydro or thermal power systems in case of the load frequency control. Okay, so this is a diagram of the load frequency control. If you anybody is interested, then you can go in the more detail. So this is one of the design I analysis on the thermal or hydro plants. Hydro plants also have the non-minimum phase, or in closed loop it form the unstable responses, unstable system. Design controller also handle it. Okay, or maybe the whatever you design, it handle the some other problems also in the similar fashion. Then it is fundamentally way of the or your design importance. Okay, so another perspective, if I consider in the today's constraint like cyber attacks. So cyber attack is also one of the portion today's in converter designing, okay, or in the controlling perspective. So what happening whenever you design any controllers, any converter or inverters in the power electronics or for your system operation, okay. So what happening, there is a lot of places and vulnerable points where the attackers or attackers uh, attack or may change the values, like the your power electronics components we have the in hardware also. There is your controller perspective also, switching they also change. And also one of the portion like network control, like if there is a, they will also control your network layer. So in this way also currently people are doing more and more work, and this is a one of the research, open research area in this domain also. Control perspective is also one of the another perspective with the AI. AI we are introducing, we are more interconnected with the communication channels. Okay, or more introduce the sensors or transducers perspective. Okay, smart things. It will share the detail via the Wi-Fi or like the communication network. So there is a more perspective of the cyber attacks. It introduced in the systems. Okay, so this is one of the area where you can do your work. Okay, I'm also working on these things. So in the next maybe somewhere I will talk. Then you can maybe heard about the some like the cyber attacks perspective in the mitigation of the cyber attack effect, detection of the cyber attack in the polyphonic systems. Okay, so this is from my side. If anyone have any question, and thank you to organizers for like invite me. So from audience, if anyone have any question regarding these things, we can discuss. It is open to all.
Good morning, sir.
So so I mentioned the like one of the chat box question like 10%, 20%. I mentioned the reason. Okay, so I think you heard about the my presentation. Then You listen my presentation, then it's cleared. Okay. Next, anyone have any question, please?
Sir, in the chat box, there is one question, na?
Sorry.
In the chat box, there is one question.
No questions. Hello.
Sir.
Yeah, there is no question further.
In the chat box, there is one question.
Just a minute. Okay, sir. Sir,
I think-
can we take the electric vehicle transfer function and design controller with the PID and PID? Yes, it is okay. No issue. You can check the electric vehicle transfer function, like second, third order, whatever order you have. You can design your controller, PID or PIDA controller. If you have the second order, then you can go with the polycon, similar patient, and you can handle it. Or if you have the third, fourth order, then you can maybe reduce the order and you can design this controller. Or maybe you can apply some like people are more doing on the optimization, so you can use the optimization, then you can get some response. But optimization is have the problem with the like resilience problems, and also the somewhere you moderate your results. Sometimes people are moderate in the optimization, so most of people are not refer in the hardware perspective. Actually, in the paper publication from simulation is okay. From the hardware perspective, people are less refers these things. Okay. Now, anyone? No, order of the your system based on the your like in case of the RLC, you know that RLC network we have. So then there is a capacitor or inductor. Okay, so based on the order we can frame. In the second order, like RLC in series parallel, we have the second order system. Okay, so it based on the system parameters. So what system is always you can frame in the open loop. GSHS I consider as a, like whatever the plant I consider in the open loop. Okay, so controller design for the closed loop perspective. Okay, like GS I consider in the GS simple. Okay, so there is no issue. You have controller design for closed loop actually, no?
Hello. Sir, good afternoon, sir.
Yes.
Yeah.
Sir, with your permission, can I ask one doubt, sir?
Hello.
Okay,
Hello.
okay. You can ask.
So this is
Yeah,
Dr.
you can ask in the chat. You can ask in the chat because your voice actually somewhere audible issue actually.
Yes.
Sorry, actually, there is issue with the audio actually. That's why you can ask in the chat if it is possible for you, and you can email me. Okay, no issue. I just shared my last way. Anybody email me regarding anything regarding to me, you can reach me at the mahendrak@nitj.ac.in, or maybe you can check my website drmahendrakumar.com. Okay, you can refer anytime. If you have any query, you can ask through the email, through the contact, through the WhatsApp, no issue. And this is a last my MK Lab team. Okay, so no issue. You can ask in the chat. So why to consider tolerance band only for parameter considerations? Uh, Actually, tolerance band in the every component, you see in the everywhere, like temperature you consider like 30 degree, you mention in somewhere data sheet. So there is not 30 degree, it have the some band now always. So I prefer this tolerance band as a parameter uncertainty for my perspective, because somebody ask you why you are considering only these values. Then I get the response from the after a lot of study. Then the tolerance band whatever the components have, I mean, like some of the variation in the value, like 20, like we consider one of the resistance 20 ohm, but it is not 20 ohm, it have the something else, some tolerance also there. So I consider this tolerance here. Okay, so that's why maybe some, if you have better answer, then we can discuss actually. Okay.
Still any question?
Hello, anyone?
Okay, sir. I think no question.
No more questions.
Thank you,
Okay.
sir. Thank you very much, sir. You provided very useful concept in the area of control design, mainly PID control design and PIDA tuning, coefficient diagram method, design of controller for unstable non-minimum phase systems, polynomial method, case study of different uncertainties. Thank you, sir. So thank you very much, sir. So some of the participants are requested to share your PPT slides.
No issue. They will contact me. Okay, they will contact me. No issue. They will WhatsApp me. They will email me, and they will call me. No issue. Everything is available on my website, also at my uh, institute website, as well as my personal website. So you can check whatever you need. Okay, anyone may be interested in my work, they will also maybe discuss. Okay, they will also interested in my work. They will collaborate, or someone want to maybe postdoc or PhD also, they will join us. No issue. Okay, thank you.
Thank
So
you,
can
sir.
I leave?
Okay, sir. Thank you, sir. You can do.
Okay, thank you, sir. Thank you.
Thank you, sir. Thank you.